So why are we bothering with this? Well, we're bothering with this because this allows us to create a pretty decent sketch of what the function may look like. So let's think about the information that we've obtained from this equation from building our table. Just going to sketch a graph. All this is a sketch, nothing that's going to be very well labeled. I know that my initial value is the point 050, so I can plot that. Well, what else do I know? I know that my initial rate of change is 10. So in other words, I kind of have a blast-off speed of 10. So I know that that's at least telling me it's increasing. Well, now my slope is decreasing by 6 units for every time I increase the input by 1. So in other words, if this is my slope from 0 to 1, my slope from 1 to 2, from an x value of 1 to 2, will be a little bit less steep because the slope is decreasing. And going back to the table, we see that. So we had a slope of 7, then we had a slope of 1, then we had a slope of -5, then of -11, -17, -23. So eventually, at some point, that slope begins to be negative. So it goes from 7, 1 to -5. And then it goes to -11. And then it goes to -17. And so as you can see, the slope keeps getting larger and larger in the negative direction, and hence we get this kind of curvature that takes place, which takes the graph, and with the starting positive slopes, because the slope is getting smaller and smaller and smaller, it eventually becomes negative, and the function ends up heading downwards. So if I did a better job of sketching this, I'm going to go to my graph. I have this in my y equals screen, so I'm going to set my window from about 0 to x goes to about 10. That way I at least get the coverage that's in our table that we made. And I know I need to go at least up to, start at 0, and I'll go all the way up to maybe 100, since I know my initial value is 50. Well, there it is. Look at that. So just by using the logic of what's happening to the slopes, the fact that the slopes are getting gradually smaller and then negative, I get a shape of the graph that looks kind of like this. And all I've been able to establish is what to expect on the basis of the graph alone. So how did I do that? Well, I know that my initial value is positive. So I'm just going to recreate this. I start with a positive initial value. My initial rate of change is positive, so the graph begins by going upwards. But because twice the coefficient of a is -6, that tells me that the slope is decreasing. The slope is decreasing by 6 units per unit of input. And hence I get something that eventually looks like this, and the slopes get very, 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 very steep, and the graph begins to drop back down. Well, if I also kind of extrapolated, what would it look like going in this direction? In this direction, it would kind of have the same shape, except from left to right, it's gradually increasing by less and less and less and less, reaches a maximum point, and it starts to come down, 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 down. And that's really all we try to do by understanding these coefficients. So let's do one more example. So in this particular instance, we have years since 2000 and the NFL player average salary in thousands of dollars. So I'm going to pull up my calculator, and we're going to look at the change. Now we know that these are 1-year increments, so what I'll put over here is my change in the salary per change in year. So my units are going to be $1,000 per year. And I'll just leave that right there. So I know that from 2000 to 2001, the average salary went up, and it went up to $992 minus $791. Tells me that I have an increase in salaries of about $201,000 per 1 year. That's a pretty nice sized increase, right? From 2001 to 2002, I have an increase from 992 to 1153. And so that represents an increase of only 161. So skeptics might be saying at this point, wow, well, it looks like the players are going to go broke because their salary increases aren't as big as they were last year.